Section 3.1, Pre-Calculus. You should be on page 3 of your packet, and we are going to be looking at the natural base e. We're going to be looking at functions with using the number e, and also some compound interest and continuous interest. All right, we're going to look at a new number. This number it's irrational. If you guys remember what an irrational number is, it's a number that does not terminate or repeat. So as we consider the case like with pi and other symbols like that, we use the symbol e here for this natural base e number, and the number is approximately 2.718 and so on. Okay? Similar to 3.14, it's another number, it's a number e. And we're going to go ahead and see where that number is generated from. The exponential function with base e is called the natural base exponential function. It is f of x equals e to the x. This is what that is. Note that 1 plus 1 over x to the x, so this is an exponential growth here. This approaches the number e, and that would be the 2.718 number, as x approaches infinity. So as I substitute x values in here and in here, as I substitute large x values as it goes to infinity, then this expression slowly approaches the 2.71 or the e number. All right, so here's what we can do. We can go ahead and use our calculator, and we're going to evaluate. We are going to find f of 1 and f of 10, and we're going to fill in this table. So if you want to pause this video, you are going to be substituting into this formula. I'll give you an example here on the f of 10. We're going to do 1 plus 1 over 10. And we're going to raise it to the 10th power. So I want you to pause the video, go ahead and evaluate all of these. You could, use your table feature as well if you'd rather do that. All right, here's what we've got for our results, and you can check the table values out, but you can see that as we input values, it does slowly approach this e. And e, again, is the symbol that we're going to use for this exponential growth. All right, here are some applications that will, slowly work towards using this e. Develop the compound interest per year as follows. We're going to let a sub t be the amount in the account after t years. So a is the amount. P would be your principal, how much is you're putting in. And R would be your annual rate. All right, and the amount would be the end amount. So after 2 years, A would tell us how much is in the account after that time. All right, I'm not going to generate this formula for you here on this video. I'll have a third video that will, if you want to look to see how the formulas are derived, I'm going to just go ahead and give you the formula so that we can use it. So again, if you want to look at a second video here, you can do that on how this formula is derived. Here's our formula for finding compound interest. The amount is principal times 1 plus rate to the t, where t represents time, r is rate, p is principal, and a is the amount. So here's our formula again down here at the bottom. This would be for compound interest, where interest might be compounded quarterly or monthly or daily, and then you can see the difference between that formula and this one. A equals P, the 1 plus R to the T power is this, the difference is this N. And the N is how many times it's being compounded in a year. So if you're asked to compound something quarterly, that's 4 times in a year. Monthly would be 12 times, daily 365. So the N is the number of pay periods. Number of pay periods in the whole year. And T would be number of years. Obviously having a little problem with my cursor today. Number of years. But we're going to use this for compound interest. I'm going to go and take you through an example with the $5,000 at 6% in 10 years, and we're just going to do several different ones. I'll work one through with you, and then the second one I'll let you guys do. All right, an investment of $5,000 is made into an account that pays 6% annual interest for 10 years. Find the amount in the account if the interest is compounded annually, quarterly, monthly, and daily. Let's go ahead and look at what we would do for annually. Annually would be for one time. So you've got your 5,000. 1 plus the rate. Our rate is 0.06 over n, and n would be how many times? So in this case it's 1. And then you raise it to a power of 1, n times t. T was 10 years, 1 times 10. So you're going to calculate this, and when you type it in, you will get 8,954 point, I'm going to go ahead and round it off to the nearest cent, 24. So that is how much is in the account after 10 years. All right, I'm going to go ahead and set the next one up for you so you see the difference. So for compounding quarterly, quarterly means every 3 months, so 4 times, $5,000 times 1 plus 0.06 over 4 raised to the 4 times 10. Now if you're putting this in your calculator and you do 4 times 10 here, you'll need to have parentheses around that. Make sure that all of the power is in the parentheses. And the result of that is 9,070 and 9 cents. All right, here's what I would like you to do. Pause the video here and go ahead and calculate for monthly and daily, and then you can go ahead and check your results with me. Here are your results of the interest, and here's something that I want you to notice. You can see that the interest, the more you compound it, the more often it's compounded, the more interest you're going to get. However, there's something else I want you to notice. If we go from annually to quarterly to monthly to daily, it's getting bigger, but it's also getting larger by a lesser amount. So between 89.54 or so, we can see that we have almost an increase of roughly 110 or so, and then between 9,070 to 9,096, it's an increase of about 26, and then we've got an increase of about 14. And so the more that it's compounded, it's increasing at a smaller amount. What we're trying to work towards is compound interest continuously rather than by some actual specific amounts. So note that as n increases, so does a, but the rate of increase slows down, and that's what I was just talking about. All right, I'm not going to derive this formula at this point in time. I'll have a video for that if you're interested. Let's go ahead and go to the continuous formula. Here's how you find compound interest if it's compounded continuously. It's A equals P for principal. So A is the amount. P is the principal. e to the, now this e is our number e to the RT. So it's PERT. I always remember PERT for our compound interest. So R is the rate and T is time. How many years? All right, let's go ahead and look at an example. So it's A equals PE to the RT. A equals PE to the RT. Continue example 4 with the interest compounded continuously. You got $5,000. Let's do it algebraically first. We've got 5,000. So A equals times E to the rate's 0.06, so 0.06 times T, which is times 10 years. And when we go ahead and go through that and calculate, you're going to see that we will get $9,110.59. $9,110.59. You can see it's fairly close to compounding daily. That amount's very close to it. Now here's what you would do graphically. You'd want to set your domain up, and your domain starting at 0 years, maybe go to 20 years, and then you could do zoom fit. Once you type your function in, the function that you would type in would be this: 5,000 e to the 0.06 and times the x, or times t, where t is the number of years, so y equals that. Here's what you'd notice. You're going to notice that your graph will look like this. It's going to look like this. It's just an exponential growth function, so you can see here your window show it increasing. And so in order for you to figure out after graphing for the 10 years, is you can evaluate at 10, so trace 10, or you could also use your table and be able to figure out your result. And the result would give us this same amount here. All right. We've got one more problem here to go ahead and go through. It says complete the table to determine the balance A for $12,000 invested at a rate R for T years, compounding continuously if R is 2.5%. So we got 12,000 times E to the RT 0.025, and T being my number of years. And so here's what we've got. If you would like to graph this in the calculator and do your domain starting from 0 at least past 50, and then you can use your table feature, I want you to evaluate this and see how much the account will have. Go ahead and pause the video, and I will come back and show you what the results are. So you're just going to substitute each of these years in, 1, 10, 20, into your variable T. Here's your end result. A lot of this you're going to be able to do in your calculator. I'm going to stress that when you do enter things, you need to make sure you include parentheses here around your exponent. Otherwise, it's not going to do your order of operations correctly. This is the end of section 3.1, and here is your assignment.